Performance analysis for AWGN and Rayleigh fading channel under different and/or fusion rules. Abstract, cognitive radio, which is a buzzword in radio technology world. The main features of the CK having low-cost communication, restrict the interference of the unlicensed users, able to fill voids in the wireless spectrum, increase the spectral efficiency, able to make final decision about primary user whether present or not. The advantage is that this technology allows the CR users to cooperate by sharing their informations for detecting the primary users. However, the accurate detection factor will be compromised if the users experience deep shadowing or fading effect. Hard decision, or rule and rule, is also performed at Fusion Center, FC, in CR. The main motive of this project is to investigate performance of cooperative spectrum sensing scheme, which is considered as the key technology in CR. Finally, this study will also show how to promote sensing performance in AWGN and Rayleigh fading channels. The performance of the CR is evaluated in terms of the probability of PMD and the probability of PFA. Then, the report is compared between the theoretical value and simulated result. After that, it describes the relationship between SNR and the detections. At last, the method, energy detection and simulation and result are discussed. Keywords: fusion rule, rock curve, AWGN channel, Rayleigh fading, complementary rock, simulation. Introduction. Modern years show an extraordinary demand for wireless communications. Due to extending the field of wireless communication, this results in more spectrum resources being required to achieve our obligations. The allocation of the spectrum usually fixed for organization, and today's spectrum management is regulated by our government. However, this leads to a common problem with spectrum wastage. 1. Some licensed bands and organizations are found spectrum scarcity. The purpose of cognitive radio has been proposed as a means to overcome spectrum scarcity and proper spectrum utilization in wireless communication. According to the Federal Communication Commission, FCC, many licensed users that are not properly utilized, remain indolent. The FCC also exposes that spectrum utilization hardly ever crosses 35% at any given time in the large populated urban areas too. The main concept behind the cognitive radio, CR, is to ensure the proper utilization of those underutilized spectrums without interfering with the licensed primary user, PU. The CR system allows the unlicensed users, also called secondary users, SUS, to use the temporarily unused spectrum that is not currently used by the licensed primary user, PU. Spectrum sensing is a fundamental component of the CR system. The spectrum sensing enables the ability to sense the presence of PU and the parameters related to the radio channel. There are several spectrum sensing techniques that have been used to determine the existence of PU, such as feature detection, energy detection, and matched filtering detection. The energy detection technique is widely used because it does not require any prior knowledge about PU. As there are some fundamental characteristics of wireless channels, such as multipath fading, shadowing, and noise uncertainty, a CR system may unable to detect the presence of the PU. To address this problem, the cooperative spectrum has been proposed 3, with the collaborative decisions of several secondary users, SU, for spectrum sensing 4, and this is done in a fusion center, FC. The FC receives signals from unlicensed SUS and combines these signals to get the final decision about the presence of PU. There are, at present, 3 fusion rules to determine the availability of the free spectrum. They are the N rule, or rule, and majority rule. Among these 3 rules, energy detection gives improved sensing performance when using the OR fusion rule. 2 methodology let N denote the number of users sensing the PU. Each CR user makes its own decision regarding whether the primary user present or not, and forwards the binary decision, 1 or 0, to Fusion Center, FC, for data fusion. The PU is located far away from all CRS. All the CR users receive the primary signal with same local mean signal power, i.e. all CRS form a cluster with distance between any 2 CRS negligible compared to the distance from the PU to a CR. For simplicity we have assumed that the noise, fading statistics, and average SNR are the same for each CR user. We consider that the channels between CRS and FC are ideal channels, noiseless. 5. Assuming independent decisions, the fusion problem where K out of N CR users are needed for decision can be described by binomial distribution based on Bernoulli trials, where each trial represents the decision process of each CR user. With a hard decision counting rule, the fusion center implements an N out of M rule that decides on the signal present hypothesis whenever at least K out of the N CR user decisions indicate. Assuming uncorrelated decisions, the probability of detection at the fusion center is given by 1. A. Logical N rule. In this rule, if all of the local decisions sent to the decision maker are 1, the final decision made by the decision maker is 1/6. The fusion center's decision is calculated by logic and of the received hard decision statistics. Cooperative detection performance with this fusion rule can be evaluated by setting k equals n in EQ, 4.1. 2. B. Logical or rule. In this rule, if any one of the local decisions sent to the decision maker is a logical one, the final decision made by the decision maker is 1/7. Cooperative detection performance with this fusion rule can be evaluated by setting k equals 1 in EQ. 3. C. Or fusion rule. In this rule, if any one of the local decisions sent to the decision maker is a logical one, the final decision made by the decision maker is 1. Cooperative detection performance with this fusion rule can be obtained as 9. 4. Squaring. Integrator. Device. Figure 1, Energy Detection. 3. Discussion and simulation results. Networks of cooperative energy detectors in the AWGN and Rayleigh fading channels are considered where an AND or fusion rule are simulated. For the hard decision, we present in following figures the complementary ROC curves of the AND and the OR rule, and compare it to the detection performance of a single CR user. For the simulations, we consider 4 CR users. Figure 2, complementary ROC under AWGN channel for an AND or fusion rule, SNR equals 10 dB, U equals 5. Figure 2 shows complementary ROC under AWGN channel for an AND or fusion rule where signal-to-noise ratio 10 dB and time bandwidth product equals 5. Figure 3, complementary ROC under Rayleigh fading channel for an AND or fusion rule, SNR equals 10 dB, U equals 5. IJERT 9 IS 090066 www.ijert.org. Figure 3 shows complementary ROC under Rayleigh fading channel for an AND or fusion rule signal-to-noise ratio 10 dB and time bandwidth product equals 5. N rule has lower probability of false alarm, but also has lower probability of detection. On the other hand, OR rule has high probability of detection, but also has high probability of false alarm. Now, OR and N rule are studied. We define values from 0.01 to 1 with increasing 0.1. The information of local detection from each cognitive radio users are forwarded to Data Fusion Center and combined to obtain final decision. The simulation is performed by using probability of detection as a metric at different SNR values are shown in Figure 4, Figure 5.6.4, Figure 6, and Figure 7. We assume 4 CR users are collaborated to detect primary user signal. Figure 4, complementary ROC under AWGN channel for an fusion rule, CR equals 4, U equals 5. Figure 4 shows complementary ROC under AWGN channel for an fusion rule where cognitive radio user 4 are considered for simulation. Figure 5, complementary ROC under AWGN channel for OR fusion, CR equals 4, U equals 5. Figure 5 shows complementary ROC under AWGN channel for OR fusion, CR equals 4, U equals 5, are considered for simulation. Figure 6, complementary ROC under Rayleigh fading channel for an fusion rule, CR equals 4, U equals 5. IJERT 9 IS 090066 www.ijert.org. Figure 6 shows complementary ROC under Rayleigh fading channel for an fusion rule, CR equals 4, U equals 5, are considered for simulation. Figure 7, complementary ROC under Rayleigh fading channel for OR fusion rule, CR equals 4, U equals 5. Figure 7 shows complementary ROC under Rayleigh fading channel for OR fusion rule, CR equals 4, U equals 5, are considered for simulation. Figure 4, Figure 5, Figure 6, and Figure 7 describes the probability of misdetection by employing an AND OR rule. As shown in the figure that OR rule has better probability of detection than AND rule. From Figure 4 to 7, it is clear that S probability of false alarm M is low, OR fusion rule has better probability of detection than AND fusion rule. As probability of false alarm increases, OR and fusion rules show similar results. At SNR values less than 10 dB, OR fusion rule exhibits better detection performance than AND fusion rule. As shown in following figures, the OR rule has better detection performance than the AND rule, which provides slightly better performance at low than the OR, because the Data Fusion Center decide in favor of when at least one CR user detects the PU signal. However, in the AND rule, to decide of the presence of a primary user, all CR users must detect the PU signal. From the figures, the OR fusion rule shows a better performance compared to AND fusion rules. This is attributed to the fact that OR decision fusion rule involves result of a minimum of a single user out of K energy detector nodes to declare the availability or presence of a PU. Though AND fusion rule indicates a slightly better performance at low as compared to the OR rule, as seen from the figure. Since the OR combining rule minimizes communication overhead attributed to its property of sending a minimum of a single decision to the FC, this fusion rule will be adopted in the rest of the analysis for cooperative users in the various channel models under consideration. For conclusion, we have studied the spectrum sensing performance in cooperative and non-cooperative environment in both non-fading AWGN channel and Rayleigh fading channel. We have used energy detection method to detect the PU. We also used OR fusion rule here. We have seen that the energy detection performs better in the non-fading channel over fading channel in non-cooperative environment. We also observed that, when CSS was considered, sensing performance improved over a Rayleigh fading channel compared to AWGN channel.